This talk is sponsored by the Central Node of the Commonwealth Cyber Initiative. It's a state program establishing Virginia as a global center of excellence in the cybersecurity research arena through supporting research, workforce development, and innovation at the intersection of cybersecurity, autonomous systems, and intelligence. Each year, CCI and CVN sponsor research and experiential learning projects, and today's speaker, Dr. Elks, is a recipient of some of that funding. It's our honor today to welcome Dr. Elks. He's a distinguished figure in the realm of safety assessment and fault tolerance. With more than 2 decades dedicated to the analysis, design, and assessment of dependable embedded systems, Dr. Elks has left an indelible mark on the critical infrastructure domains in nuclear power, medical systems, and autonomous vehicles. Throughout his career, he has propelled the state-of-the-art of safety assessment, cybersecurity, and fault tolerance and resilience. He's a recipient of the National Technology Transfer Award from the Federal Laboratory Consortium, and his expertise extends to resilient cyber physical systems, systematic SW testing, and runtime verification and monitoring, fault injection, cyber threat and vulnerability, and modernization strategies for energy and utility infrastructures. Today, he'll unravel the intricacies of cyber physical resilience for security, safety, and integrity assurance in devices, and explore the challenges and solutions in ensuring the safety, security, and integrity of those devices. Please enjoy this presentation and be sure to stay on after for our Q&A session. Dr. Elks, I turn it over to you.
Hey, thank you so much, Jen. Yeah, it is an honor to be here with some of my colleagues and some of the people who are working in the Central Virginia node and our industry partners as well. Yeah, as Jen noted, today we're going to talk about essentially cyber resilience and what that's all about. We're going to kind of delve into, the differences a little bit up front about cybersecurity and cyber resilience, the complications of cyber resilience realization, and some potential solutions we're looking at least in my lab. But like I said, the first part of this talk, we're going to kind of again set the backstory about like why we're kind of again looking at this particular issue for kind of again medical systems. Of course, cyber resilience is much needed in a lot of different areas, particularly in the kind of defense systems these days, where it's getting a lot of kind of again play in that regard. So again, I'm Carl Elks, Associate Professor. The co-PI of this work also, Dr. Milos Manic is working with me on that. And of special importance, who's also going to be on the talk today, is Jake Wegman, who is the Senior Lead Designer at Caretaker Medical Systems. He's our industry partner on this work. So without much further ado, this is sort of the kind of, again, the outline of what we're going to talk about, a little bit of background. We're also going to talk a little bit, I'll give Jake a little bit of time to talk about, an actual, what it's like to kind of, again, develop medical systems and stuff, and the complications resulting from that from the point of view of cybersecurity, compliances, how do you actually address that while you're trying to build cost-effective and very functional medical devices. And then we're going to talk about sort of the research, kind of again, we're doing right now on this for CCI. And then where do we want to go from that? So again, here's the important people. And that in that context, I think, like I said, I mentioned all of the students, of course, are very important. These students are basically shared between my lab and Dr. Milos Manic's lab. I'm not going to go into, if you really want to kind of begin after today's talk, want to kind of like dig into some of this, these are publications that are strongly related to the work we're going to talk about today in that regard. So, yeah, the big picture, um, as you can see from this kind of again slide here, it is essentially a heavily driven both cyber physical system, IT enabled system and virus. It involves a lot of systems, people, and information flows in healthcare systems. And one of the challenges we have in kind of again securing these systems is not a lot. These systems don't often want to play nice with each other, meaning they're not meant to be highly integrated, even though they're getting better at that. And this is one of the reasons why we have sort of kind of again some complications related to kind of again securing these systems in that regard. As we begin to kind of again look at this work, we needed to kind of think about, well, what is a medical computing platform? So we're talking about cyber resilience, and there's a sort of a kind of like a generic way to think about this. And so we have adopted sort of a kind of like a generic medical computing platform from essentially Proctor. And this is, kind of again serves our purpose to us thinking about what all the information flows that could happen, the databases, the displays, the applications that are on the actual kind of again processing kind of platform, the interactions with essentially operators, nurses, and clinicians and stuff like that. So this just serves for us, meaning the researchers, what what is our context that we're going to be working with when we think about cyber resilience? So anyway, I'm not going to go into a lot of this, but there's lots of kind of again things you need to kind of be concerned about with medical cyber physical systems, and not all of these things have to do with kind of again just security, but they have to do with fault tolerance, reliability, safety. All of these things are closely integrated together in that regard, in that context. So yeah, so a lot of times we think about, well, if you look out into the world or you just pay attention to on a sort of monthly basis on the number of systems that have been compromised, hacked, or breached, it seems like it's always increasing, and it's always kind of again spectacular and stuff. But how did we get to this place is an interesting, kind of again philosophical discourse that we won't go into. But Gary McGraw, who some of you may or may not know, he's a fairly famous cybersecurity expert that's worked with just about everybody, coined this term called the Trinity of Trouble, which is now also called the foursome of trouble. And he says, as our digital IT systems and operational technology systems in software kind of again exploded in the 1990s and the 2000s, there were four attributes that started to kind of again like contribute to this notion of kind of again difficulty in securing system. One is complexity, and the first one here, complexity. Software-enabled systems are just become really complicated. I mean, one of the things you can you look at in terms of that, well, not even today's, like mid to 2010, 2015 car has more software in it than your laptop, okay, in terms of lines of code. It's just, we're talking about millions of lines of code in your car to essentially for the entertainment systems, for the environmental controls, engine controls, all of these things. So software has really just taken off. And on top of that, we've entered the age of machine learning and algorithms where, we have very complex kind of again software that's difficult to understand or explain. The next one, extensibility. Yeah, all of our modern IT software systems and even cyber physical systems are built to be extended, meaning that essentially they do these updates on your system over the internet or over a web and asking you if you need new features, or sometimes not even asking you, in updating your firmware and stuff like that. This particular facet allows essentially new software to be loading into you without you having full awareness of what that is. And of course, connectivity, everything sort of these days is connected. Now, it may not be connected directly to the internet, but it is connected to something. The last one is the interesting one, monoculture. Monoculture essentially is we have lots of systems that essentially um, don't have a lot of diversity in them. So the kind of uniformity predisposes these systems to essentially catastrophic consequential attacks. So think Windows. The number of basically devices that use Windows in a particular environment or version of Windows, if somebody were to craft to attack that essentially could get to all of these machines and everything, they would all go down at the same time. So that monoculture is also a potentially big problem. But at the end of the day, we just want systems we can trust and depend on in cyber events. So how are we going to get there? So yeah, so we have lots of kind of again decisions to make. When you look at the last page, it just seems like really hopeless. So we can feel like Eeyore here. You know, so many possible systems to attack, so many ways to attack them. You know, and the list goes on and on. But it's not hopeless. There is a way forward. And the way forward, according to some of the big thinkers in the world right now, is we need to start thinking about cybersecurity from a systems perspective to give us these multiple kind of again perspectives about the organizations of these systems, the design of these systems, the use of these systems, so that we can kind of again have a better way of understanding what are the possible kind of again fallacies or vulnerabilities in these systems. So let's start with what's the difference between cyber resilience and security? Well, cybersecurity has been kind of again around for a while, and you can think of it like a wall or a perimeter. It encompasses all the technologies, processes, measures to protect our system. Okay, so these are encryption, firewalls, any type of security appliances, various types of things to essentially kind of again make it difficult for anyone to penetrate our system and get at any kind of again important data or compromise it or intrude upon it in such a way that it's they intrude upon confidentiality, integrity, availability, and maintainability. So that's been our mainstay for 25, 30 years, 40 years at least. Cyber resilience is something kind of again new in the past 10 or 15 years. It's like the ninja. So it's this ability to anticipate, withstand, recover from, and adapt to these adverse cyber conditions or events and stresses on compromises on the system. So it's not so worried about building a wall, even though the wall may be part of cyber resilience. But it's once somebody actually gets into your system, we want our system to be able to be, robust or resilient to recover from and adapt from what's going on. So that's the difference between resilience and security. So we started to kind of again started developing probably about at least 10 years ago, maybe longer. But it was first codified cyber resilience by the NIST, the National Institute for Standards and Technology, in 2021, where it was right there. Once it gets codified there, it becomes part of the federal kind of again, kind of corpus of documents that people will use to build systems and everything. In essence, as you can imagine, cyber resilience is a bigger thing. It's a broader approach to cybersecurity. But more importantly, it's a strategic approach. Cybersecurity is like a tactical approach. So though it's a tactic to build a wall, it's a tactic to build something to kind of again deflect or deter some type of attack onto a system. Cyber resilience is saying, hey, I want to, instead of thinking about certain types of attacks, I don't really care if I get attacked, but if I get attacked, I want to be able to do the following. Okay. So it's much more strategic and it thinks it. It begins with asking these questions about what essential services and functions have to be conserved or secured against disruptions and how those disruptions can lead to an unacceptable loss. So from the very beginning, you're starting to think about not so much hardware and software, you're thinking about the functionality of your system. So for instance, if I'm in a hospital and I lose essentially some type of connection to an important, kind of patient portal where the doctor needs that information to make decisions, that's a service that if it stays disrupted can lead to, essentially kind of again bad outcomes or at least certain losses that are going to affect somebody. So you would identify that as that function as something you need to protect, but more importantly, you need to kind of be able to restore it and recover it. That's what sort of cyber resilience is about. So conceptually and graphically, we can think about cyber resilience, in this way. Suppose, looking at the diagram here on the right, suppose I have some type of ACE, which is essentially an adverse cyber event. And the vertical line here or axis here is called a MIF, which is mission essential functions. And it's a performance. And it's just, you need some type of essentially capacity and capability to, perform your service here in this regard. That's all it's measuring here. And of course, this is time. So if you have some type of event here that's unknown, like a 0-day attack, it starts to degrade your system and or knock out your system completely. You're going to essentially go below some threshold, and then, but here's where cyber resilience is different than cybersecurity. Cyber resilience begins to reconstitute, restore, kind of begin build your system or kind of begin doing something so that it recovers. So at this stage, I'm essentially not delivering appropriate service. At the orange stage, I'm at the threshold, I'm getting stuff out, and then up here, I'm actually at fully green. I'm giving you good service at that point. So the challenge that is before, the medical community and a lot of other people working in essentially, kind of delivering cyber resilient systems is how do you build this? So this is a great graphic for explaining what you want, what a cyber resilience is, but how you actually build this and realize it is a very, very hard challenge today. Now, of course, there's people working on this, everybody is, but it is still a challenge to do this. I won't go through these, but these are the objectives that are typically that NIST lays out. And the ones that we're concerned with, at least in this research, are the latter ones. Continue, constrain, and reconstitute. So how long can I keep things going? Once I've been sort of kind of again attacked, how can I limit that damage from an adversary, and how much can I build back on that and stuff. So these are the ones that typically are important for cyber resiliency. I'm not going to go into a lot of this, but I've circled the ones that we've targeted in my lab to start working on. We have worked on and are currently working on. These are suggested resiliency techniques from the Jones model, which is some people at UVA, but NIST and others have a have a list of these resiliency techniques that you can employ in your system. But as you can imagine, just because you have a list doesn't mean you can build these systems. There's a gap in exactly how you take a list like this and how you take guidance and actually create a method to actually start designing a system. That is what the next slide kind of talks about. So for those of you, I don't know if anybody's out there has read the NIST SP 100 160 Volume 2. It's all about it's the Bible for cyber resiliency. It's like a roadmap, a detailed roadmap. It tells you how to critically think about what cyber resiliency is, how to integrate it into your organization, how to think about it, and everything. But it doesn't tell you anything about how or what. Other than at these very high levels, which it's not NIST's job to do that, but that's a gap. And part of our research here was to investigate a method that we felt like could be used to help fill some of these gaps, which I talk about here, which is called STPA. So this is part of what we're doing. So I'm going to stop here. I think, Jake, are you on?
I am.
Yeah, so Jake is, again, I'm going to introduce Jake. Well, actually, Jake, introduce yourself. And,
Sure.
And explain this diagram to us.
Sure. So my name is Jake Wegman. I'm a staff engineer at Caretaker Medical. I've been in the electronics industry for 16, 17 years now. Started as a with Agilent Technologies as a chip designer, and I've wound up in the medical device hardware and a little bit in the software space as well. Caretaker Medical, we're based here in Charlottesville. The company was founded in 2014. And as you can see from the middle picture there on the slide that you're viewing, our principal product is a unit that you wear on your wrist. And then there is a pneumatic cuff that ties to your finger. And basically think of it as a miniaturized version of, the ubiquitous arm cuff that when you go into the hospital to get your blood pressure checked. This is a miniaturized version where we are essentially sensing the perfusion in the digital arteries rather than trying to sense it in the upper arm. With the advantage being, of course, that you can't squeeze your upper arm for hours at a time, whereas if we apply just a little bit of pressure to the middle finger, we can continuously monitor blood pressure and other associated hemodynamic parameters for many hours continuously at a time. So what you can see in this diagram here is we have many different ways to monitor a patient's various health parameters. So it starts with our VitalStream wrist-worn unit there that then talks to what it's showing there is an application running on an Android tablet that displays waveforms both coming from the unit and other devices that are connected to the system. So, what we're showing in this diagram here is a temperature patch that you may be wearing on your chest and an SpO2 meter that you're wearing on another finger to monitor blood oxygen levels. A doctor may put an ECG on you to monitor the electrical signals in your heart. So we have Bluetooth channel for monitoring that particular parameter. And then we have various ways of connecting to health information systems. So your hospital will have some kind of electrical or electronic medical records keeping system. Our system can communicate with those. We have our own system that we can sell you that will allow you to, record that data. There are all kinds of different communication channels here, wireless channels that are passing data back and forth. So yeah, I think that kind of covers the whole system.
Yeah, I think, and again, I wanted everybody here to look at this is very typical of medical device type technology today, where you have multiple information streams, multiple different contexts of those information streams, multiple people interacting with it, multiple entities interacting with it. So these are not your typical like embedded systems. These are more like system of a system. Okay, so in that way, we've got to look at these from the perspective of like how can they be essentially compromised, and we need a systematic way to do that, and that's kind of the next sort of again discussions as we move forward. So our research challenges that when we looked at this are, how do we systematically decide on like what is the appropriate resilience technique, in that regard, and even before that, how do you decide on what are the kind of perceived hazards or cyber events that this system could encounter in its world and stuff. And this leads to context. Context plays a big role in all things related to safety and security, and it will do so probably in cyber resilience and stuff. So these are some of the sort of kind of questions we're asking as we sort of want to explore like cyber resilience on medical device platforms. Yeah, so the research strategy, of course, was aim one. Aim one is like thinking about what's the method to systematically find cyber hazards and cyber events, because that's going to drive everything. And of course, the next thing we recognized is you need to have almost pervasive monitoring of your systems to determine when things are changing, or you potentially could be exposed to cyber events, or something is going wrong that is sort of unexpected in that context. So we knew that, and how you do that is quite challenging as well. And the last is, we need to design, implement, and evaluate certain of these selected solutions and think about them in the context and collect data on them. And of course, Caretaker is a large part of helping us kind of again do this. And in what does Caretaker get out of this? Our cybersecurity and cyber resilience solutions and ideas go back to them, okay, for their technical basis. So it's each of us are getting something out of it. It's a win-win. So yeah, so STPA stands for System Theoretic Process Analysis. It is basically a hazard causality model. It's used mainly to kind of identify hazardous conditions and states sort of proactively. So you might be you might kind of again been exposed to like fault tree analysis, HAZOPS, FMEA type things. Those are all similar type methodologies used in sort of kind of again reliability analysis. STPA is a relatively new, like last 13 years, I think it's been on. STAMP and STPA have been in, and it looks things differently. So the ones I just mentioned are like forward looking. They mainly look at when something fails, like a fault tree analysis, an event tree, an FMEA, a HAZOPs, like if something fails, meaning a component fails, what's the consequence of that? So it's like forward looking. It's like if this breaks, then that breaks, then it causes this, blah, 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 up to the top event, and then the whole system fails or doesn't fail. SDPA is almost like an iterative control system process. So they realize that accidents are more complicated than, and particularly in today's systems like what we were just looking at with Jake's caretaking system. They involve complex dynamic processes that need to be evaluated in terms of like these feedback loops. And it captures many of the causes of accidents. This is the important one. It captures the failure accidents, but it captures also accidents when nothing fails. Okay, so those are like design flaws. So if it's like you missed something in the requirements or specifications and about how the system operates, and there are many of those types of kind of, again, failures today. In fact, they're becoming the predominant failure today is, you've missed some type of key type of condition or things in the requirements, and it's omitted, and it experiences that out in the world, and the system can't handle it, and it just basically fails in that regard. Flawed requirements. Okay, so SDPA is actually really good about doing that and stuff. And I won't go too much. It's I point you to some literature to do this, but we've embedded sort of SDPA in a workflow we developed about 6 or 7 years ago with the University of Virginia. Dr. Barry Horowitz, Peter Beeling, myself, and Cody Fleming. And it's called Mission Aware. And the whole idea between Mission Aware is that you have to identify your critical assets and workflows up front that have significance to sort of the system and mission resilience. And we build sort of models of the system. And here we for reasons I won't go into, we turn them into sort of meta models. And these meta models are compared to what are the opportunities of an attack with respect to resistant resilience. So we built a tool called CyBOK that allows us to sort of kind of, again, look at databases of certain cyber kind of again vulnerabilities and see if our system has potential susceptibility to those. And then we look at sort of what are the consequences of the attack. So now we get into SDPA. It's like what are those particular problems that could occur, and then from there we can look at essentially how we're going to refactor the architecture to affect the adversary's ability to exploit or affect the target system. So this is a fairly what's called a mission oriented type of framework for cyber resilience. And that's what we are going to use on this particular work on a couple of different targeted, what we call mission essential functions. The next type of aim or work that we're working on this is, of course, I mentioned monitoring. Cyber resilience, it won't get very far off the ground if you don't have this ability to sort of know an understanding of what's going on in the system. Okay, a central component of cyber resilience is that persistent, reliable understanding of system context in state, in which requires us to do that. And from another piece of work that which is based in actually at NASA, it borrows from the NASA work we did for urban air mobility flight vehicles, is the notion of pervasive monitoring. And pervasive monitoring is built upon two things. One is context monitoring in a vehicle here, but in our case, it's the medical device monitoring types thing. Context monitoring assesses the environmental and kind of, again, operational context, the modalities. All hazards almost always get triggered when context and strange system states combine together. So you have to have this notion of actually what's going on in the outside world. And the system application monitoring assesses what's going on inside the device or, in its user and cyber physical state. And fusing these two things together, we call that pervasive monitoring and stuff. Okay. So this is something we think is going to be very important for cyber physical systems resilience. Yeah, so this is just an example of what context is in the context of systems. It's information that is not directly mapped to a system state, but is still associated with it. And the example here is braking action applied to a given on a car. Okay, so on a normal road, for you in order to stop before you hit the rear end of somebody's car, it might be, a delta T of like, 2 seconds. But if the roads are snowy, wet, or icy, those braking conditions completely change because of the context of the road. Okay, so now it may be, 10 times that and stuff like that. So I can't really measure, or it would be difficult for me to measure the friction coefficient of the road. But I can kind of infer it, based upon, the sort of kind of notion of it's either wet or icy outside. So it is observable. It may be potentially measurable, but it's not controllable. I can't control the ice on the road. So that's what context essentially boils down to. So I'm looking at our time here. I want to kind of move through these. This is just our methodology for generating essentially monitors. We believe the monitors that we're going to develop come in 2 different flavors, these context-aware monitors and these other multi-level monitors that sort of fit at different places in this. The important thing about context-aware monitors, we think they're going to be we know they're going to be data-driven. They're going to be like machine learning type monitors. So this is just an example of a high-level example of what a context-aware is in a medical device. So you could have essentially a PCA pump, which is essentially a pain pump, and you could have essentially these 2 essentially sensing systems here connected to essentially kind of again a combined vitals to determine if it's time to release some type of analgesic to the patient and stuff. And so you would want to measure this context, the CO2 levels and O2 sats, and maybe there's other things. And you want to also sort of determine what's going on inside the device, okay, at this particular time as well. What's its state? You combine these 2 things together, and that's basically context-aware monitoring. And context-aware monitoring allows you to have some bigger notion of what's going on in this system. So this fits in with Jake's world and the whole idea that we need to have essentially this pervasive monitoring kind of again paradigm. Last but not least, this is the last part, is like, how do we move from kind of again these resilience, from monitoring to resilience patterns? So in this work, we're not going to have enough time to go through all the resilience patterns that I showed in the previous. There's 14 of them, but we've located a couple that we think are really important. One of them is diversity. Diversity tends to show up a lot when you're trying to kind of make it difficult for your adversary to kind of penetrate your system. So remember, I talked about monoculture. So if you have 2 different platforms, controller A, one is from implementation 2, supplier 2, and everything. This would be, a completely different set of attack vectors for this one and this one. So it would theoretically, my adversary would have to spend a lot more effort and time to compromise my system to do this. So the downside to this is obvious. It's very expensive to do this, and you would only use it in, in high criticality and integrity systems. But we're looking at another approach that looks at essentially diversification of code and computation that may be much more effective, but we don't know yet. And that's the next slide. So with our partners at UVA, Dr. Jason Heiser, who's done a lot of work in Link Lab on essentially diversification of binaries, meaning creating diverse binaries from a single application. So the way that they do it is, I won't go into that too much, but it's like genetic diversity in biological systems. The code, the binary code changes enough that it's the same. The attack on variant 1 or version 1 might not work or will not work on version 2 or version 3. So it's enough variation in these binaries here that it won't be susceptible to that type of infection and everything. That's essentially the postulate right now we're working on. There's some good evidence that this postulate holds. And then the last one we've added to this is on certain sort of system on a chip where you have FPGAs, you can actually create an entire hardware version of a function over here in addition to these. So this diversity in a I won't go into too much, but this is what's called the zipper tool. It's developed by UVA that allows us to create these versions of code over here and everything. And so how are we going to use that? So there's these things called systems on a chip, and there's a lot of different ones, but the ones that we're going to think about using are from the Xilinx Zinc architecture, where we have different, we have 2 cores here and 2 cores here, meaning processors. We can actually get the binary code, diverse binary code to execute here. We can get the diverse hardware variants executing here, and kind of realize these types of function. Now, how you essentially organize and create this and build a resilient architecture is to be determined. But the idea here is that if you can do it, could be really cost effective compared to this, where I go out and buy 2 different things and to get my diverse redundancy and stuff. So anyway, so I'm going to stop there. We're about getting close to the end of the time. It was actually a little bit over. So this is a work in progress, everyone. We're working on these frameworks, on this, and in inclusion, we hope to advance this knowledge base a little bit further down the road. Specifically, we hope that SDPA turns out to be a useful methodology for assisting us on the identification of cyber hazards and appropriate mitigation selection techniques. And that also we hope the same for context-aware monitoring as well, in that regard. So, and then hopefully all this stuff, some of it will be useful to caretaker medical in that regard. And so I will end my talk right there for today. And I will be glad to turn it back over to Jen for questions. And that's about it. Thank you very much.